guys, let's talk about Hess's law today. That sounds exciting, doesn't it? So Hess's law is where we're talking about combining the enthalpies of different reactions. So remember in the past we've talked about that chemical reactions aren't always one-step processes, that there can be multiple steps. Well, each of these steps has their own enthalpy or heat of reaction. So let's take a look here. If a reaction can be expressed as a series of steps, then the delta H, or heat of reaction, for the overall reaction is the sum of the heats of reaction for each step. And so here we see that we're defining step 1 with its own heat of reaction 1 right here. We have step 2 with its own heat of reaction right here. And that we're saying the overall heat of reaction, which they're defining as 3 here, is these two things combined. And so we can bring them all together. And that's what Hess's law is about. Now, there's some other parts of Hess's law. We have 3 different pieces to think about when we're talking about heat of reaction. So the first one is when a reaction is reversed, the enthalpy is the same in magnitude but the reverse in sign. This makes sense. If a reaction is moving forward and it's exothermic, it's giving off heat, then when it moves backwards, it's going to need that heat to go in and is an endothermic reaction. So our delta H is going to go from being negative to being positive in that situation. Of course, we can have vice versa there. Number 2, when reaction coefficients are multiplied or divided by a factor, the same factor in operation applies to the enthalpy of the reaction. What I tell students is treat energy as a reactant or a product, depending on the type of reaction we have. So let's say we have an exothermic reaction, then just treat the energy like another product. So if you're dividing the whole system in half, all the coefficients in half, then you would divide the energy as a product here in half also. So you treat energy just the same as you would any other reactant or product. Number 3, when 2 or more reactions are added to obtain an overall reaction, the individual enthalpy changes of each reaction are added to obtain the net enthalpy of the overall reaction. So basically, if we have those steps that we're breaking the chemical reaction down into, that our net reaction is going to have the net amount of energy. Now, one step could be exothermic and one step could be endothermic, and so we just have to watch which was greater, and that makes our net enthalpy for the net reaction. And we're going to take a look at that right here. So here we have a nice example, and we have our net balanced chemical equation down here, and we see that there are 2 steps to this overall reaction. And we see the first step is exothermic, and the second step is endothermic. But when we look at this final step, we need to make sure that our first and second steps connect to our complete overall reaction. And so when we look here, we see that in our first step, nitrous oxide is a reactant, when in our overall reaction, it is a product. So I'm going to get out my writing tool here, okay, and we would be reversing this first step so that it matches our overall reaction. So we would actually use this as N2 plus O2 resulting in 2NO. Okay, so now we see that our NO is a product and our NO is a product. Cool. And then we look at our second reaction here, and we see that our NOCl is a product when we want it to be a reactant. So we need to flip this guy too. Should have gotten out my little tablet instead of using my mouse to do this. And I should be writing those phases in there, but I don't have a lot of room. So being a bad role model right now, for you guys, you write it in. Okay, so we flip these things. So remember, we treat energy just the same as the chemicals. So here, this would have been a product. Well, now it is a reactant, so this is positive, as we can see here, right? And we flip this guy, so he was a reactant, and now he is a product, okay? All right, so now we can go through. I'm going to change the color here. And we can go through and we can cancel things out. You remember doing this in prior lessons to make sure that we end up with our sum equation. So we have 2 NOCl, excellent. But here we have N2O2 as a, we have N2O2 as a product and as a reactant, so they can cancel out. And we end up with 2NO and Cl2 as products. And our N2O2, they are spectators, right? They're not actually involved. We start with them and we end with them, so they're not actually involved in that reaction. All right, so we can take these guys and we do our math here. We have plus 180 minus 103, and so our heat, our overall heat of reaction is 77.2 kilojoules. All right, here's 2 more examples. Please pause the video and look them over. All right, so some things to point out that hopefully you noticed a little different from our prior example is that for this one, for our top one, we have a flip, but we also need to half it. We have 2 moles here, but we only have 1 mole here. So that means that we needed to half this entire step, and that means that we also half the energy. Remember, we treat the energy just like we would a chemical. And then for this guy, we didn't need to half them because we have our product in the step and our product in the sum equation. However, we see that we have 2 here and we only have 1 here. So this one also needs to be halved, but we keep the same sign. And so that one's halved and we do our math there. For this guy, 3 steps, so a lot to think about as we organize them. Remember, we want to line things up, right? So for example, here we have methane, but we have methane as a product, so that guy needed to be flipped, and we see that by we change the sign there. This one, we have NH3 as a product, we have NH3 as a reactant, so we know it needs to be flipped, and we see that we have a 2 to 1, so it needs to be flipped and divided in half. Here, this one, we see that we have product and product, awesome, so we don't have to switch the sign, but we see that we go from a 2 to a 1, so we do need to divide in half. So it's really matching up what's in the steps with that sum equation. If you have a 2 to 1, you're going to divide in half. If you have a 1 to 2, you're going to multiply by 2. If you have a flip, you're going to switch the sign. Okay, here is another example. Looking to see if there's anything different about this one. Oh, that you have hydrogens in different places, and so you can combine them. That's the difference there. Same methodology. All right, here's a video. Go ahead. Watch this video.
This problem given two reactions. Carbon monoxide reacting with sulfur, S2, and COS reacting with oxygen. And the question is, we have this information where we know the heat of reaction for these two reactions. Can we determine the heat reaction for oxidation of S2 to make SO2? Essentially what we want to do here is apply Hess's law, which says if we add reactions together, we can add their heats of reaction. In this case, we want to use these two reactions and add them together to get reaction of interest. Now, to get the equation, you notice we have two oxygens in the reaction that we're interested in, which means we have to take this reaction times 2 plus this reaction times 1 and add them together. See, when we do that, let's write it out completely first. So left side of first reaction plus twice the left side of the second reaction. Then on the right side, first reaction term, and then twice the products of the second reaction. And we notice this is on the same on both sides, and carbon monoxides is the same. So we end up with the reaction that we're interested in. So this means we could take this heat reaction times 1, this heat reaction times 2, add them together to get the overall heat reaction. So the overall heat reaction is minus 192 plus 2 times minus 265. 6 kilojoules. So the overall heat reaction, this reaction then is minus 722 kilojoules.
So this video thinks of the problem linearly and takes the steps and brings them together and combines them into a whole linear equation and then cancels things out. I demonstrate things more vertically and list things in succession and then cancel things out that way. Total preference, whatever works for you. You'll get the same answer either way. All right. Like you to pause the video and try this one on your own, and then we'll talk about it. Okay, so hopefully you saw that we didn't need to flip either of our steps, but that the second step needed to be divided in half. And where we first see that is that our product right here, we have 2 and we have 1. And so I put my thoughts in the purple color, and so when we give everything a half, we see that this guy is like we're saying that there's 2 over 2. So we combine that to actually thinking that there are 3 over 2 oxygens. And then we also see that we end up with half the sulfurs there too. So I'm sorry, we end up with half the SO2s, and then these guys can cancel out. So there we go. And so when we half the energy, of our second step. We end up with this as our total heat of reaction. All right, let's take a look at this one. Please pause and try the problem. Okay, so this one was much harder. Where I start with is I do my flopping, my switching first so that I'm lining up reactants with reactants. So like here, I see that I have an NO2 and I have an NO2. So the first thing I do is I switch those and I get those all lined up. And then I look at how many of everything I need. And of course, the hard one was this 3/2 and then 1/2 because we have to think about that oxygen in two places. So in our first step, we end up with 3/2 of an oxygen. And then we end up with 5/2 in our second step. So combined, we end up with 4 oxygens, which are then removed, right? Yes, we end up with, let's see, so we have 3/2 here and 5/2. So we end up with 1 oxygen in our reactant, and then we can cancel it out because we have 1 in our product. So the oxygens were hard to follow. That one is pretty challenging. And then we make sure that whatever we do to the equations, we also do to our energies, and then there's our total energy. Alrighty, let's take a look at the next one. Pause and give it a try. Okay, so here we see step 1. We don't need to do anything to. Whew, that makes it easier, right? The second one, we see we need to flip that guy, and we need to divide in half because we want to only have 1 N2O, right? And so, oh, I'm sorry, I skipped there for a second. In our second step, we want to have 1 NO2 right there, and we have 2, we want to go to 1, so that's how we get the divide in half. We also see that this is product, and we want it to go to reactant, and that's how we get the flipped. What I started talking about too early was we see this guy, we have the N2O as reactant, and in our net equation it's reactant, so we don't need to do the flip. However, we have a 2 to 1, so we know we need to divide. And we have 2 in the step, and we have a 1 in the complete equation, and that means we need to divide by that number. And then we see that we are actually endothermic, 159.5 kilojoules for our heat of reaction. Last one. Give it a try. And here's our last one, which actually looks more complicated than it is because we have 2 steps that are just about a phase change. And so we just need to make sure that our phases are matching up there. So for the second one, it stays in that order, but we need to multiply by 6. So we multiply our energy by 6. Our second one, we multiply, our step 3, we multiply everything by 3. And step 4, we need to switch it and multiply everything by 2. Step 1 stayed the same. And so when we go through, we get a very large heat of reaction, positive 6,338.8 kilojoules. So that's a lot of energy to go in there. So this guy requires some energy to make it happen and is very endothermic. All right, guys. Thank you very much. That's Hess's law.